Hello everyone, let us start symmetric matrix and skew-symmetric matrix. We have already discussed about transpose of a matrix. So what is transpose of a matrix? If we interchange the rows and columns of the matrix, then we get a transpose of this matrix. So skews next come to symmetric matrix. So first of all, symmetric matrix is a square matrix. So a square matrix is called a symmetric matrix if A transpose equal to A. That means the general form of a matrix is, we can write the general form of the matrix is Aij. If Aij equal to Aj, then the matrix A is called symmetric matrix. So for example, 1, 2, 3, 2, 5, 6, 3, 6, 8. If this is a matrix A and this is also a square matrix, so let us find out this is a symmetric matrix or not. So we have to find A dash first. So A dash is equal to 1, 2, 3, 2, 5, 6, 3, 6, 8. So this is same with matrix A. So here A is equal to A dash or A transpose. So this matrix A is called a symmetric matrix. Let's come to the skew-symmetric matrix. So skew-symmetric matrix is also a square matrix. If the transpose of a matrix is equal to the negative of the matrix, then the matrix is called skew-symmetric matrix. That means a transpose or A dash is equal to minus A. So in general form, the elements, if the elements are in form of Aj, means if A has the elements Aij, then A dash has the elements Aj. So if Aj is equal to minus Aij, then this matrix A is called skew-symmetric matrix. If we will take here I equal to J, then from this we get Aii. Aii is equal to minus Aii. So from this we get Aii is equal to 0 for all elements of I. That means all the diagonal elements are 0. So a skew-symmetric matrix having the diagonal elements are 0. So for example, A is equal to 0, E, F, minus E, 0, G, minus F, minus G, 0. See this matrix, all the diagonal elements are 0. If we take A12 element, this element, A12 element is E, so A21 element is minus E. If A13 element is F, A31 element is minus F. So this is a square matrix and all diagonal elements are 0. All each Aij equal to minus Aj. So this matrix is a skew-symmetric matrix. Let us prove two theorems. So come to first theorem. First theorem is for any square matrix A with real number entries. This is applicable only for real number entries. A plus A dash is a symmetric matrix and A minus A dash is a skew-symmetric matrix. We have already discussed symmetric matrix means A transpose is equal to A. So here first of all let B is equal to A plus A dash. If B is equal to B dash, that means transpose of B, then B is called a symmetric matrix. That means A plus A dash is a symmetric matrix. So now we will find here B transpose, that is B dash. So B dash equal to A plus A dash of whole dash. So that is equal to, we know already, A plus B whole dash is equal to A dash plus B dash. So we can write here A dash plus A dash of dash. So that is equal to A dash plus A. So we know that the matrix satisfies the commutative rule. So we can write here A plus A dash, that is equal to B. That implies V dash is equal to B. So B is a symmetric matrix. That means A plus A dash is a symmetric matrix. Let's come to second part of this proof. A minus A dash is a skew-symmetric matrix. We have already discussed if A transpose is equal to minus A, then A is called a skew-symmetric matrix. So let C is equal to A minus A dash. If C transpose is equal to minus C, then C is called a skew-symmetric matrix. That means A minus A dash is a skew-symmetric matrix. So let us find out the value of C dash. So the C dash is equal to A minus A dash of whole dash. So that is equal to A plus minus A whole dash. So that is equal to A dash plus minus A whole dash. That is equal to A dash of dash. A dash minus A. So here we can write minus A dash. So here we get minus C. So C dash is equal to minus C. That means C is a skew-symmetric matrix. So here A minus A dash is a skew-symmetric matrix. Let us prove theorem 2. So theorem 2 is any square matrix can be expressed as sum of symmetric matrix and skew-symmetric matrix. Let us prove this. We can take here A is any square matrix. So we can write A is equal to 2A by 2. So 2A means A plus A by 2. So here we add this term A dash and subtract A dash. So that is equal to A plus A dash minus A dash plus A whole into half. So this is also equal to half whole into A plus A dash plus half whole into A minus A dash. So any square matrix can be written in this form: half whole into A plus A dash plus half whole into A minus A dash. We have already discussed A plus A dash is a symmetric matrix. A plus A dash is a symmetric matrix. So here we multiply half with this A plus A dash. That means this is a scalar multiplication of matrix. So half whole into A plus A dash is also a symmetric matrix. Similarly, we have already discussed A minus A dash is a skew-symmetric matrix. skew-symmetric matrix. So that half whole into A minus A dash is also a skew-symmetric matrix. So A can be expressed as the summation of a symmetric matrix and a skew-symmetric matrix. This can be proved by taking one example. Let us take one square matrix. So here A is any square matrix and we can express this A is the summation of symmetric matrix and a skew-symmetric matrix. We have already discussed A is equal to half whole into A plus A dash plus half whole into A minus A dash. Here half whole into A plus A dash is a symmetric matrix and half whole into A minus A dash is a skew-symmetric matrix. Let us take P is equal to half whole into A plus A dash and Q is equal to half whole into A minus A dash. If P is equal to P dash, then P is a symmetric matrix. If Q dash is equal to minus Q, then Q is a skew-symmetric matrix. Let us prove this. So first of all, we will find the value of A dash. So A dash is equal to 2 minus 1, 1, minus 2, 3, minus 2, minus 4, 4, minus 3. We get here A dash. Now P is equal to half whole into A plus A dash. So this is equal to half whole into 2 plus 2 is 4, minus 2, minus 1 is minus 3, minus 4 plus 1 is minus 3, minus 1, minus 2, minus 3, 3 plus 3 is 6, 4 minus 2 is 2, 1 minus 4 is minus 3, minus 2 plus 4 is 2, minus 3 is minus 6. Now we get 2 minus 3 by 2 minus 3 by 2 minus 3 by 2, 6 by 2 is 3, 1 minus 3 by 2, 1 minus 3. So this is equal to P dash. So P is equal to P dash. So P is a symmetric matrix. So we get here P is a symmetric matrix. Now come to Q. So what is Q? Q is equal to half whole into A minus A dash. So half whole into A minus A dash. 2 minus 2 is 0. Minus 2 plus 1 is minus 1. Minus 4 plus minus 4 minus 1 is minus 5. Minus 1 plus 2 is 1. 3 minus 3 is 0. 4 plus 2 is 6. 1 plus 5. 1 plus 4 is 5. Minus 2 minus 4 is minus 6. Minus 3 plus 3 is 0. Now get here Q is equal to 0, minus 1 by 2, minus 5 by 2, 1 by 2, 0, 3, 5 by 2, minus 6 by 2 is minus 3, 0. Now we get the value of Q. So Q dash is equal to 0, half, 5 by 2, minus half, 0, minus 3, minus 5 by 2, 3, 0. Now we get, see this matrix and this matrix, here Q dash is equal to minus Q. So Q dash is equal to minus Q, that means Q is a skew-symmetric matrix. So here P is a symmetric matrix and Q is a skew-symmetric matrix. Now you will find the addition of P and Q. So P plus Q is equal to, P is equal to 2, 3 by 2, minus 3 by 2, minus 3 by 2, minus 3 by 2, 3, 1, minus 3 by 2, 1, minus 3. plus q is equal to 0 minus half minus 5 by 2 half 0 3 5 by 2 minus 3 0. Now we'll find the value of p plus q. So that is equal to 2 plus 0. P plus q is equal to 2 plus 0 is 2. Minus 3 by 2 minus 1 by 2. That is minus 4 by 2. Minus 3 by 2 minus 5 by 2. Minus 8 by 2. Minus 3 by 2 1 by 2. That is minus 2 by 2. 3 plus 0 is 3. 3 plus 1 is 4. Minus 3 by 2 plus 5 by 2 is 2 by 2. 1 minus 3 is minus 2. Minus 3 plus 0 is minus 3. So we get here 2 minus 2 minus 4 minus 1 3 4 1 minus 2 minus 3. Here we get this is A. So P plus Q, that means summation of symmetric matrix and skew-symmetric matrix is equal to the given matrix. So we get any square matrix is a summation of symmetric matrix and a skew-symmetric matrix.